All right, if you're an engineer, you know that being able to precisely control light is basically a superpower. I mean, whether you're designing sensors, fiber optics, or the next generation of displays, you have to master how light works as a wave. So in this explainer, we're going to break down the physics you absolutely need to know about gratings and polarization to really get the job done.
Okay, let's just dive right in. Here's our game plan. We're going to start with the absolute basics. What happens when a light wave hits an opening? Then we'll see what happens when we scale that up, which leads us to some incredibly powerful engineering tools. And finally, we'll talk about another way to control light.
First things first, we have to get a really solid grip on what happens when a light wave meets some kind of barrier. Because it's not just about blocking the light, it's about what happens on the other side. And that leads to this fascinating and honestly crucial phenomenon called interference.
So, what is interference? At its core, it's just waves adding up or canceling each other out. When light waves squeeze through a narrow slit, they spread out and start to overlap. Now, where the peaks of those waves line up perfectly, boom, you get a bright spot. We call that constructive interference. But where a peak meets a trough, they cancel each other out, and you get a dark spot, and that's destructive interference. Simple as that.
So let's start with the simplest possible case, light going through just one single opening. Now, you might think it would just create a sharp little rectangle of light on the other side, right? But nope. It actually diffracts, creating this foundational pattern, a really bright, wide band in the center with these much dimmer, bright bands off to the side. Getting this basic pattern is step one.
Now, here's the part that should make every engineer really happy. This pattern isn't random. It's perfectly predictable. This formula right here, it's the recipe. If you know the light's wavelength, lambda, the distance to the screen, L, and the slit width, A, you can calculate the exact position of those dark spots. Let's just run a quick example. For the first dark fringe, we get 1.2 millimeters. For the second, 2.4. See that? The spacing is a consistent 1.2 millimeters. This is what we love to see, measurable and repeatable.
And this is where things get really interesting. When we add a second slit, the whole game changes. Instead of that one wide central band, we get a whole series of equally bright and equally spaced fringes. The formulas change too, and notice this. The key variable shifts from A, which is the width of the slit itself, to D, the distance between the slits. This is our first big clue that the arrangement of the light sources is what really starts to matter. So we've gone from one slit to two. The logical next step is to see how this builds, right? What happens if we take that double slit idea and just scale it way, way up? We're not talking 3 or 4 slits. I mean thousands, maybe even tens of thousands, all packed super close together. So this leads us to that classic engineering question. If 2 is good, is more better? Are we actually gaining something significant by adding all those extra slits? Are we building a more powerful, more precise tool?
And the answer is a huge, resounding yes. I mean, this image just captures it perfectly. As you increase the number of slits, those bright fringes become incredibly narrow, sharp, and way more intense. All those fuzzy, spread-out bands you get with 1 or 2 slits, they're gone, replaced by these beautiful, distinct peaks of light.
But why does this happen? Well, with more slits, you have way more individual waves interfering. In all those spaces between the sharp peaks, you now have thousands of waves all arriving just slightly out of phase. This massive amount of cancellation just obliterates the fuzziness, and it forces almost all of the light's energy into those few perfectly defined bright lines. And this very principle, using a huge number of slits to create these super sharp peaks, this gives us one of the most important tools in all of optics and electrical engineering, the diffraction grating. So think of a diffraction grating as the ultimate multi-slit device. It's an optical component that's designed to do one thing, and do it exceptionally well. Split light into its constituent colors, or more precisely, its different wavelengths. It's kind of like a high-tech prism.
Okay, but there's a really important detail to get here. Right in the center, directly in front of the grating, you have what's called the zero-order maximum. At this one spot, light from every single slit has traveled the exact same distance to get there. Because they all arrive perfectly in step, they just add up, and no color separation happens. So if you shine white light on it, that central line is also going to be white.
And this is where it all comes together in the real world. The absolute heart of a modern spectrometer, a device we use to analyze light, is a diffraction grating. It takes whatever light you shine on it and neatly separates it out into a rainbow of its component wavelengths. By measuring the intensity of light at each of these specific positions, engineers can create a unique spectral fingerprint. This is how you can do amazing things, like identify the chemical makeup of a distant star, measure pollutants in the air, or calibrate the color on a high-definition display. This is precision measurement at its absolute finest. Now, not all gratings are created equal. They generally come in two main flavors, and the one you choose really depends on your application, specifically whether you want light to pass right through the device or bounce off its surface. And this slide shows the two types perfectly. On the left, you've got a transmission grating. Think of it like a series of tiny parallel windows. Light goes through it. On the right is a reflection grating, which is basically a mirror with thousands of tiny parallel grooves etched into it. Light bounces off these grooves and then interferes. So the key takeaway here is pretty simple. While the end result, splitting light into a spectrum, is the same, the physical mechanism is totally different. One works like a set of tiny windows, the other works like a set of tiny angled mirrors. Both are absolutely essential tools in an engineer's optical toolkit. Now, splitting light by its wavelengths, that's one powerful form of filtering. But there's another fundamental property of light that we can filter for. This gives engineers a completely different knob to turn, and it's called polarization. So what exactly is polarization? Imagine a light wave coming right at you. Its electric field is oscillating. It's wiggling up and down, side to side, or at any angle in between. Unpolarized light, like from the sun or just a regular light bulb, has waves vibrating randomly in all directions. Polarized light has been filtered so that all the waves are vibrating in just a single, unified plane. What's important for us as engineers is that we've got several physical ways to actually do this filtering. We can use special materials that literally absorb light vibrating in one direction. That's exactly how polarized sunglasses work. We can use reflection. You know that glare off a road or a lake? That's partially polarized light. Or we can even use refraction, because light can become polarized when it just passes between two different materials. So we've covered how to separate light by color using gratings, and how to filter it by its orientation using polarization. These are the fundamental building blocks for controlling light, which, of course, leaves us with the final and really the most important question for any engineer. With these incredibly powerful tools in your hands, what are you going to build next?